Yeah, so welcome everyone. After this nice introduction into Perseus, I will start now with the first tutorial, and this is going to be really the basics. So how to upload a matrix, how to do the first transformations and everything. And keep in mind, Perseus is really designed for the users. So you don't need to be a bioinformatician or a statistician to interpret your data. Perseus is really designed for the biologists, the chemists, the medical people who want to analyze their own proteomics data. And Presales is not limited to proteomics, actually. I think Jürgen and Pavel already made that clear, but it's also suitable for analyzing all kind of omics data. Of course, it's optimized to analyze the data that were generated by MaxQuant. But as I said, it's in principle, it's open to all kind of omics data, and it's also a great platform to combine the different omics data. So we start with the very basics, how to get Perseus. So you just Google for Perseus, MaxQuant, and then you will eventually end up here at this homepage. You just go to download, you fill out the form with your email address and your name. And then after that, you will receive an email with a link for the download. And then you end up here, you end up with a zip folder. Here, you end up with a zip folder, and then you unpack it, and then basically Perseus is ready to start. So then you end here, Perseus, and then you just go to the application and you start the application. So I already did one Perseus session, but we will start from the very beginning again. Just keep in mind, so one question always comes up, and this is the question. So you cannot open, once you did a session with Presales and you saved it, you cannot open it with a newer version. And of course, people are complaining, but the reason for this is that we're constantly improving the software, we're fixing bugs, we're adding new features. And since we're not a commercial company, we cannot keep track that this will not cause any conflicts at the end. So the best thing to do here is that you really, once you have your zip folder, store it somewhere, you'll find it again. And then I would also recommend just to save the name of the version with your file name when you save your session, so that you can reopen it every time again, and with this Perseus version. So the data set we are analyzing today is a data set that was created by Tammy Geiger, who gave this basic tutorial about Perseus in the MaxQuant Summer School in 2018. And you will receive, after the summer school, you will receive a link to get the data so that you can do the analysis for yourself on the very same data set. But for now, yeah, it's not available. Since this data set was created by Tammy Geiger, please do not ask us any specific questions about the data set that we cannot answer. But we know that it is, we can have a look now. It was from a SciLac experiment with different cancer cell lines. So what you get as an output in the protein groups table of MaxQuant will be ratio heavy to light labeled and normalized. And as you can see here, we have here different cell lines. For every cell line, we have 3 replicates. And it's also for later, it's important to keep in mind that this data set we're using today is a sub data set of a much larger data set. When you don't have SciLac data, but other types of data, let's say, for example, a label-free quantification, you won't have those ratio HL normalized, but you will have the LFQ intensities, and this just works the same then. So now we can really start with uploading our data, as you can see here. So this is the whole, Perseus, how it looks like when you open the application. You have here the basic things like saving, opening a new session. You have tools, annotation download. This will be useful later on. A window you can rename your session, and then there is the help button. First thing we will need here is this here to load the matrix. Then we have here processing. So you see you have many tools, but do not worry. Daniela, Schule, Shivani, and I, we will take through every step. Then we have here the analysis, and also here buttons for export and multiprocessing. When you do an analysis using Perseus, you see that you create a workflow. And this is actually really nice because you can follow every step you did in this workflow. And it's also nice if you want to explain your supervisor or if you want to explain your collaboration partner what you actually did to analyze those data. And it's also really nice because Perseus never overrides a matrix. With every step, you create a new matrix with the changes included. But this also means if you do a mistake, you can simply go back, you can delete what you did so far, you can simply go back to your original matrix and start all over again. And so I would say we start now uploading this data set. So we go here to matrix, load, generic matrix upload is usually what you need. And then you can go here. So we go to select. And then we have, as I said, this breast cancer cell line. And what you need is the proteins group output table coming from MaxQuant. You can have here text files or comma separated values, but yeah, the default thing is then the text file. So you go to open. And as you can already see here, Perseus already assigned the type of that the column has. So we have here the main columns. Main means, okay, these are actually the data we're doing our analysis on, basically. So these store all the information about our data. We have the numerical columns, so some more information about it. The categorical columns will be really useful when filtering our data. And keep in mind, Perseus does not decide whether something is a contaminant or not. This is all done by MaxQuant. And if you want to change something about the contaminants, you have to go back to MaxQuant. So Perseus is not the platform to do this. And then as Jürgen explained, you have the text column that give you additional information, but you don't want to do any analysis on text. It might be when you're opening your text files that actually those here are not automatically assigned. So it could be that all of your different columns are listed here. And then you have to decide what is the column I need. So as I said, for Silac data, the main column is stored, is the ratio heavy to light labeled normalized. For the LFQ data, the LFQ intensity and so on. But you can find on our documentation website, you can find a more detailed explanation with which type of data sets you have, which type of data. So, but if the columns are all listed here on this left panel, you simply select the columns you need, and then you can switch them using this arrow here to the, for example, here now the main part, to the numerical part, to the categorical part. So you can decide, yeah, you have, if it's not done automatically, you have to decide which type of column it is, but you can change it later on if you find out you did a mistake. So, and now we go to OK. And now you will see here, okay, we have here now generic matrix upload. This is also really nice in Perseus because it really shows you, okay, what it does. So with every step, so you can follow easily, okay, it did this thing. And now we have this new matrix here. Especially when the workflow gets more complicated, it's always useful to rename the columns so that you know with one look into Perseus, okay, what was this step about? I mean, it also tells you here, rename, filter, and so on. But it's also nice to rename the columns, rename the matrices. So you just go right-click here and you give it an alternative name. Let's say, for example, unprocessed. Okay. Don't forget to save your sessions in between, just to be on the safe side, because yeah, I mean, we all know with software, sometimes we run into problems and then we lose everything, and you don't want to lose your whole workflow. Then, yeah, we simply start. So we have now the unprocessed matrix, and maybe the first thing we want to do is actually we want to rename the columns, because here, as you can see, we have ratio heavy to light label normalized for all of those, and this is not really informative. So we had to increase here the space to read it, and so on and so on. So we know it's a Silac data set, we know what we did, so maybe we want to rename the columns. So first thing we do is we go to rearrange, and we can go to rename columns. And now you can see you can give any column you have, you can give a different name. So you can just manually delete it. Okay, and we press OK. But yeah, this would be a really tedious process if we want to do this for all 9, or if you have an even larger data set, we don't want to do this manually for all of those. So for now, And now I will also show you how to delete it. We can simply delete this matrix here. Are you sure you want to remove it? Yes, I want. I remove this one as well. Keep in mind that it's not possible to remove from the middle, which makes totally sense, because if you remove from the middle, all the stuff down here will be also kind of, will not work out. So you remove from the bottom and you go up to the top. Now we want to rename again, but this time we want to do it in a more organized way. And if you want to remove the same expression in any of those columns, you can go to rename column on regular expression. And what you can see here is, so now we have to type in a pattern. And if I do this now, you see here, I type in ratio. You will see here what is the current name of the column, and you see here the columns that are affected by this change. And $1 means just, okay, you replace the regular expression ratio now with nothing basically, so you just remove it, and you will see here that those columns are affected and they will no longer have the name ratio HL normalized, but HL normalized. And then we can go on. Normalized. And now you can see here, okay, if we type in this regular expression, we just end up with this, and this is what we want to do. And again, you see you have created a new matrix here. But you can see, so here we also get on the side information about this matrix. So we have 9 main columns, we have categorical columns 3, we have more than 9,000 rows. And this, of course, hasn't changed because we just renamed it. The next thing we do is we want to filter the rows, because, as I said, so we have categorical columns, and we want to filter out those proteins that do not meet our quality criteria, or actually contaminants. So we go to filter rows and we say, okay, filter rows based on the categorical column. And now you have this window here, and now we had 3 categorical columns, and so we have only identified by site, reverse, or contaminant. So we just start with the first. So only identified by site. If this is true, it doesn't meet our quality criteria. So we just put this one on the side here, and here you have a mode. You can remove the matching rows, what we actually want to do, or you can keep the matching rows, which we don't want to do in this case because we want to filter out those proteins. And then you have the filter mode. In this case, yes, we want to reduce the matrix. Okay. And then now you can see here that while we had here 9,144 rows, we end up here now with 9,032 rows, which is quite good because this is around 100 rows we filtered out, and this is pretty normal. If you have really high value here when filtering based on these categorical columns, you should probably think if something went wrong with either the max quant analysis or with your sample preparation even before, because it's not normal that you have so many proteins that do not meet the quality criteria usually. And then we go on, we filter based on categorical columns, only identified by site, we already did. So we go now for reverse. There is only one value assigned to this, either a plus or nothing. So everything that has a plus here, again, we want to remove. We say, okay. Now about the contaminants, I told you this is already assigned by MaxQuant if this is a probable contaminant, and you can change in MaxQuant what you consider as a contaminant or not. Usually contaminants are, for example, proteins on your skin, keratins that fall into your sample during the preparation from your face or whatever, from your hair. But it might be that you have a biological setup where these keratins are actually pretty useful, or you need it for the analysis. So you can either do, so I will do it later, again, filter out all the contaminants, which are usually the keratins, but what you can also do is you can manually filter. And you can, for manually filter, you need this, select rows manually. So you click on this hand, you click done here on this hand, and now again, you have your matrix, and you can now select, for example, here, the first row, yeah, it's assigned as a contaminant. So we say, okay, this one is a contaminant. And now you can say, remove the selected row or keep the selected row. So we say, okay, move the selected row. And now you see here, it created a matrix. This one here had 8,943. And this one here is now 8,942. So we just removed this one row. But for now, we want to remove all the contaminants assigned by MaxQuant. So we just go back to this matrix here. And this is also the nice thing. You can do stuff now in parallel. You can do it this way or the other way around. And then we go here again to filter rows based on categorical columns. You say contaminant. OK, we want to filter out those. And then we enter with a matrix and has now filtered based on all the categorical columns we have. So we save in between just to be on the safe side. The next thing you want to do, maybe you want to transform somehow the data here in your main columns, because, for example, here in the SciLab experiment, we have now the ratio normalized heavy to light labeled, but we want to have it the other way around because this makes more sense from the biological point of view. So to have the light to heavy labeled. And what we do now is we can go here to basic and transform. And then we can here any equation you want to have, you can type in here. Log2 is the default one, and I will explain you in a minute why. But for now, we want to do a different transformation. So I'll show you now this here, just for those, so that it's easier for you to follow. So at the moment, we have heavy to light labeled as a ratio X, and now we want to switch the ratio. So basically, we just do this transformation. And to get the switched ratio, we need 1 divided by X. OK, so this is what we do now. We go back to basic. We go to transform. And we say here, OK, 1 divided by X. And then you can see here, so Perseus automatically assumes that you want to do this on your main columns, which makes totally sense. But in principle, of course, you could also do it to other columns that are numbers. So we say here, OK, we want to do this to those. And yeah, now we switched it and we can easily, so here this was below 1. And this one is now above 1, so seemed to work. Of course, you cannot test this manually for all the rows, but you can trust Perseus that it did the right thing. So we do now a second transformation, and as I told you already, so the log2 transformation is the default one. And why is this the case? So now we have those ratios, and of course, so a ratio, if nothing has changed, the ratio is 1. If something has heavily changed towards the light side, basically, you have a ratio of, I don't know, 50 or maybe even 100. If the heavy labels are heavily enriched, you might have a ratio of 0.25. And the ratio of 0.25 and the ratio of 4, it's actually the same fold change, just in different directions. And you can, but without doing this log transformation, you cannot really assign it. And also you want to have, if there is 0, you would think, okay, basically nothing has changed. But at the moment, that's not true. If you have 0, you have really heavily enriched the heavy labeled ones. So what you do now is the log2 transformation. Show you here, because this then allows us, so we have light to heavy labeled, and if this is 1, if you do the log2 transformation, then you will end up with the exponent here, which is 0, and this is exactly what we want. If nothing has changed or hardly anything has changed, it should be close to 0. If the light to heavy labeled ratio is 2, then the exponent is 1 after the log2 transformation. If the light to heavy labeled ratio is 0.5, which is exactly the same fold change, just in different directions as above, we will have as an exponent the -1. And that's why you need to do really this log2 transformation, because also later for the analysis, it's based on this, that you did this transformation. So this is what we do now. We go to basic, transform, and this is why it already tells you, okay, the log2 transformation, this is a default. In principle, of course, you can also do other logarithmic transformations, but the log2 is the most intuitive one. So we do this one to all of those. And now we end up here with this log2 transformed matrix. And now you can nicely see. So here, for example, in the second row, we had 0.19, and you don't really have a feeling, is this a big fold change or not? Because if it's going below 1, yeah, we lose our feelings for those numbers. And now after the log2 transformation, we can easily see, okay, it's minus. So the heavy levels are enriched here in this case. And now, but what you can still see here, we have a lot of rows where actually we did not detect the protein, so not a number or only in a few of those. And as I told you already in the beginning, this is a sub-data set of a much larger data set. So we will have many, many rows where the protein is actually not detected in the cell lines we are looking here, but this was the case for the other ones. And that's why maybe we want to, or not maybe, but we want to get rid of those proteins that have not assigned a number. And that's why you go back to filter rows, and then you say, okay, now filter rows based on valid values. Actually, you can also say here, okay, the values should be valid. This is what we want to do now, but you could also say greater than, greater or equal, less than, less or equal, between, outside, whatever. And we want to reduce the matrix. Then we can decide here. So the mode in total means that for all of our main columns, this should be the rule up here should be applied. Meaning if we have in total, and number 3 means, okay, in at least 3 of our main columns, we need to detect those protein, or a number has to be assigned. And then we want to filter it out. You can also change it to a percentage, for example, 70%, which means now in 70% of our main columns, we need to have a number assigned for this protein, otherwise it will be filtered out. And this is now a case where you really have to think about what makes sense. We will do this now in total for the purpose of this tutorial, but it might very well be that the protein is expressed in one of your cell lines and in the other not, or for example, you have a knockout and the wild type. Of course, if you say in 70% of the main columns, the protein must be present, you will filter out exactly the protein maybe you're interested in because you knocked it out for half of the samples and for the other half not. So this wouldn't make sense. That's why we have also here, we can decide in each group or in at least one group. And if we say now in at least one group, okay, we're running into problems because how should Perseus know what group we mean? We didn't have a grouping yet. So what we do now is we say in total, but I will show you in a minute how to do the grouping then. So percentage, 70% in total. We say, okay. And now you can see here, whereas we had here 8,774 rows, we end up here now with less than 4,000 rows. So this was a major filtering step. But now, as I said, okay, maybe it doesn't make sense to filter it out here in total. So we go back here, and then we want to add. So we want to do an annotation row, meaning this here is an annotation row, and we have here the main columns, main, and we want to do a categorical annotation row. And then we can do this here. We can say replicate. And then you can see here the columns. And now for all of the same cell lines, we want to have the same value assigned. So we can simply say here, okay, we want to have the same value for all this, for the same cell line. We want to have the same value here. So we go there and we change this to that one. And then you see, okay, we have here now the same value. So we do this again here. And then also for the last one here. Okay. Okay, and then now you can see here. Okay, I just heard that many people are asking when we have LFQ data, what we should do now. Luckily, I have prepared something for this. So if you have LFQ data, you can simply, this one. So for example, this was a huge, or maybe I just do it again. Okay, we did, here now we did this grouping. Maybe we finish this one for a second and then we go back to the LFQ data. So as you can see here, we had more, so we had 8,747 rows here. After the total filtering, we ended up with 3,500 roughly. And now when we did this different type of filtering here, oh, we didn't do any filter, we just, yeah, this we do now. So we can go back, filter based on valid values. And then we say, okay, now number, and we say 2. So out of the, and then we say now in at least one group, which means, okay, for the same cell line, we have 3 main columns, and at least 2 of them, we need to have those protein assigned with the number. And if we do this one, and we don't care if it's present in the other ones or not, because this is maybe something we want to find out. So the grouping is now based on replicates. So we defined this group and we say here, okay. And now you can see here, whereas after this total filtering step, you end up with 3,500. We end up here with 5,300. But this is really a step you have to think about what makes sense for my data, what is meaningful, and yeah, of course everyone has to think about him or herself for the data sets. Now coming back to the questions with the LFQ data. We can also, so let's just upload here. And this data set I cannot provide you because it's a personal one. Here, again, we have the protein groups table. And now you can see here, okay, Perseus assigned some of the columns, but not all of them, but probably we don't need all of them. And now for the LFQ data, you go to the LFQ intensity. So you just say, okay, the LFQ intensity for all of my samples. Again, we had different, or we had the same cell line, but we had different treatments actually. So A, A2, A3 is the same cell line, same treatment. B is the same cell line, but with a different treatment and so on. So you just put these ones here, say, okay. And then you say, okay, here, again, we have those categorical columns only identified by site, reverse, potential contaminant, protein IDs, and so on and so on. And you just go for okay. And now we have this matrix here. And now basically everything is the same as for the other data. Of course, you do not switch the ratio. So you do not this 1 divided by X transformation. But in principle, the filtering based on the categorical columns, the log2 transformation, the filtering based on the valid values, this is all the same. Okay. And now basically we are at a step where we uploaded it. We did the basic transformations that you later need to do all the statistical analysis and everything. So the basic stuff has been all done, which is part of this basics tutorial. Now maybe we want to visualize our data a bit. So we go back to this matrix here. And now we want to visualize. And here you have many options. And here they explain you briefly when you go through to them, they explain you briefly what it is. So here we can draw histograms. And histograms are really useful because they can give you a really nice overview how your data are distributed. So we go on this histogram button here. And of course, we want to do this for the main columns. So all three different type of cell lines. And here the 3 replicates. And we say, okay. And now you can see here, we have an inlet here, and this will show you the histograms. And now we just switch this a little bit. Okay. So now we have the histograms. And then maybe we want to change something. So we want number of columns. Number of columns just means, okay, how many histograms are displayed side by side. So we go on those. At the moment we have 2, but we want to have 3 maybe. Okay, now you can see all the same cell lines. They are listed here like this. And then, yeah, this is now 3 is better here because we have 3 different cell lines. So it's assigned like this. And now, so this histogram basically shows you how the fold changes are distributed. So of course, for a lot of proteins, we don't have any change. That's why they are around 0. There are some proteins that are going more towards one side, and here we can see those, and to the other side. So these are on the left side here. And as I already said, Presales is really designed for the users, not for the bioinformaticians. So the default parameter settings are most likely to be already give you valuable information, and you don't need to think about it too much. But of course, it's always useful if you know what you do and why you do it, and think about how to process them. So number of bins means, okay, in how many bins should this be divided? And the default setting is 21, and this looks pretty good. But of course, you could also say, let's say we want to have 4 bins. Okay, then we go to 4 bins. And then we end up like this. But of course, this doesn't give you so much information because yeah, you have a really large bin here around the 0 and you don't really see the distribution. Of course, you can also say, okay, I want to go much higher. Let's say we go to 100 bins, and then you can see even a much better distribution. But as I said, so 29, the default setting is here already. It's already pretty useful and pretty good. So this was about the histograms, and then you can see here for all the individual samples how they are distributed, if they are evenly distributed or if there are massive changes. This you could also see here. The next thing we want to do is, okay, we want to have a scatter plot for this. So the scatter plot here, you can have here the scatter plot. Okay, yeah, based on the columns. And then we end up here with the scatter plot. So the scatter plot here, now the default setting, so it compares the first two samples, which means for this cell line, replicate number 2 with this here replicate number 1 compared to replicate number 2. And you see the fold change here and the fold change here. And now as these are replicates, you can already see, I mean, if you do it for, let's say you do it for the same thing, then you see a straight line, which makes totally sense because yeah, this should be a straight line. And then you can see here, if you do it for the replicate, you can still see this correlation. If you do it for a different cell line, maybe this one, you can see that there is not so much correlation anymore. So what you can do now, let's go back to this one because this is probably more useful. Maybe you want to know the Pearson correlation, for example, to know how good your replicates are correlating, for example. So you can go to correlations, and then Presales gives you here a whole bunch of possible things it can calculate. And again, here you have to think about what makes really sense, and this also depends on the type of data. Are they normally distributed or not? Whatever. So let's say one usual thing one does is the Pearson correlation. So you just mark the Pearson correlation here, and then you go to this equation button and you say, okay, and it gives you here the Pearson correlation, which is 0.87. 1 would be a perfect correlation, 0 non-correlation. So we're pretty close to the 1. It's a good correlation, and this is expected because, yes, as I said, it's the same cell line, just different replicates. If we do the very same thing now for this other cell line here, you can already see it from the scatter plot that the correlation is not as high as before. Go again to Pearson correlation, go to this equation button, and you see here, okay, now the Pearson correlation is only 0.36, so we don't have as much correlation as before, as I said, as expected. So now, what you can do now as well is you can do here a rectangular selection. So maybe I want to select those that are highly enriched here for both of them. So you just go for this rectangular selection and you mark them. And what you can do now, you can say, okay, bring selection to top. And I have the selection now on the top. And then maybe I want to assign a different color because I want to find them again in the other scatter plots. So you go again here, you can go, let's say it's orange, it should be orange, say, okay, and now I have those here. And now when I'll go to another one here, you will see those that are, these are permanently marked orange now, and you can see how they are distributed in the other scatter plots now. It might also be that I'll want to find something. So we'll go on find what, I don't know, let's say ribosome or ribosomal. I want to find them all. I can look in the whole table, or I can say, okay, I want a symbol column, which doesn't make sense, but for example, in the protein names or in the gene names or whatever, but I want to search for the whole table. And I say, okay, find them all. And now you can see here, these are all the proteins that have something to do with ribosome, ribosomal processing, whatever. Again, you can mark them here. Just mark them all. Then you close here. And then you see these are all here. You say again, okay, bring selection to the top, and then you can assign those another column. Let's say, for example, green. Okay. And now all the proteins that are somehow assigned to ribosomal things are marked in green, and also for the other scatter plots here. So maybe you don't want to have a look at individual scatter plots, but you want to see them all. That's why you can do a multi-scatter plot. And this is here the sign, multi-scatter plot. So you just go here, multi-scatter plot. Okay, yes, I want to do this for all of those. And then you have a new tab here. And this is now the multi-scatter plot. And you can see here, okay, now you can do basically the same things. You can here, you find, maybe I want to see the Pearson correlation for all of them. So you just go to Pearson correlation and it will show you the Pearson correlation for all of them. You can go here, individual scatter plot, you just double click on it and then you see it here. And then you can do again the same things as before. You can mark a selection here. Okay. And then you will see here, okay, now we could permanently mark those, and then they will be also displayed in the different color in all of the other scatter plots. Yeah, and then basically there is only one thing left now for the basics. Maybe you want to add some annotation. So you want to know, for example, if your proteins have something to do with apoptosis or so, and this doesn't necessarily have to be in the name, but for this we have the gene ontology annotation. And so you want to add an annotation. So you go back to your matrix and then you say, okay, annotation column, add annotation. You go there. Add annotation, and then yeah, here it's already, because we already did this so that we don't have to download it. Usually what you get by default when you install Perseus, it's only this one here. If you want to have other types of annotations, for example here, Homo sapiens with all of the GO terms in it, you can go here, tools, annotation download, and this will direct you to the home page. And when you get your annotation, you need to put it here. When you are in your Presales software, you go to the bin folder config, and then you go to annotations. So, and then what you will find here is a GZ file, and then you just put it in here, and then Perseus will find it for the annotation. So we go back now, because we already, as I said, we did this so that we do not have to download it live here while giving this tutorial. Again, we go to annotation columns, we go to add annotation. Okay, and now what we want to have is maybe the GO, the biological process, the molecular function, the compartment. Maybe we also want to have the KEC, whatever. Just, okay, give me all of those. And I say, okay here. And now this takes a little bit. And you have a new matrix here. Now, one thing I just didn't check. You see, all of those are empty now, which shouldn't be the case. And if this is the case, probably what you did is you have the wrong identifier, or you have the wrong organism. But so these are all human cell lines. Just check that you're in the right organism. So, okay, now we did something wrong. So we delete again here. Yes, I want to remove those nodes. Yes, I want to remove here the annotation. Okay, let's go back here. We go to annotation, add annotation. And as you can see here, okay, the identifying column, because I mean you have to have a matching name that this can be assigned, was protein IDs. But what you need here for those is the UniProt ID. So again, you change the identifier. You go here to GO, biological process, molecular function, compartment, whatever you want, and you put them there. Okay, now we add the annotation again. Again, takes a while. And now we have this new matrix here. And as you can see nicely now, we have now assigned different things here. And again, now you could, for example, go back and you could draw a scatter plot. Okay. And when you go now to the scatter plot, you can also search here, find, and let's say we go for apoptosis. You can say the whole table, or maybe I just want to have the biological process name. Okay, find all of them. And now you can see here the proteins that have as a GO term biological process assigned something with apoptosis. So we can again mark all of those. Say, okay, now you see these are actually a lot. Bring selection to the top. And then we can assign again another color. color. And so maybe this blue one. And now you can nicely see here, okay, these are all the proteins that have as an association with the GO term biological process. And I think we're done with the basics, loading up a matrix, how to do the first transformations, how to do the filtering of your data, seeing how they correlate, the scatter plot, how it looks like. Thank you very much for listening.